So next topic, uh,
Mm.
a possible hidden planet in the Kuiper Belt.
Ooh.
Yes, this
Why
is an
only why
exciting
only
one.
possible? Why only possible?
So this was done via simulation, so they didn't discover like a
Ah,
potential, or it wasn't like the case with Uranus where we discovered Neptune because we saw that Uranus's orbit was being perturbed. So as you know, you may or may not know, solar systems can capture other planets. So there are plenty of planets just marching around the galaxy. They're called rogue planets that they don't have a host star, and if they go
or free floating.
free floating, right? Most recent discovery actually was like the JWST with the jumbos, the Jupiter mass binary objects, which are just so creepy and so cool. So solar systems can just capture free floating planets around. The question is that the study sought to answer was basically what's the likelihood that we captured one in the past, and that if there's one out there. And so they did this very interesting analysis. They basically created a simulation based on something called a mass function, which tells you basically how much free floating planet mass you're going to expect to pick up based on assumptions and other physics. It's something that's quite challenging to measure, but you can measure it via both theory and experiment by looking at other solar systems and stuff. And like what planets they've captured, if you can tell that. They've created the simulations and checked of our solar system's evolution and checked to see how many planets what we captured in the simulation and how far out they were. And they found that we captured a little over one free floating planet on average with a mass greater than Mars at a median predicted distance of 1400 AU, which is 1400 times farther than the distance between the Earth and the Sun. And so on the face, that's pretty cool. The face value like interpretation is there's a pretty good likelihood that there's a hidden planet with the mass of Mars out there in the Kuiper Belt. And so that by itself is pretty exciting.
Right. This is all theoretical, but that's
Yeah.
the prediction they're making.
It's all theoretical, right?
Yeah. So these predictions can be really sensitive to the input parameters that you use. And so it'd be interesting to see if the input parameter was off by 20%, for instance, would you still have that one potential free floating captured planet?
Yeah, so it was a fun study to read, but this is my biggest confusion with it. So I can share my screen and show some notes on this. So basically, the mass function that they use is right here, and it has this. It's pretty dominated by this coefficient, this 2.18 plus or minus 1.4, and basically, if you change this value 2.18 within the reasonable error bars, you'll get quite different answers. And that's totally fine, right? That's how science works. We do things with uncertainties. The problem was the paper didn't report how the resulting uncertainty on the captured free floating planet estimate. So
Mm.
if these error bars are really tight and you have a really good understanding of your mass function, then you might have low error bars. Like you might get like 1.2 plus or minus zero point 0.1 planets. And so that tells you, okay, this is a really robust analysis and you're likely to have, this is likely to reflect reality, at least if the assumptions hold. But the problem is these error bars are so huge and the error bars on this alpha parameter are comparably large. It's my initial, just some back of the envelope math will tell you that if you vary these coefficients, you'll end up with quite a different value. And
Yeah,
so it's
that's right.
very important to see what the error bars on that number are to assess how important this is. But the paper didn't include it, which I thought was a small, like, it could have represented a good improvement to the analysis to include
It
that.
was an oversight, maybe.
Mhm.
Yeah.
It was not just limited to that too. Also, in their like simulation parameters, like the choice of binning, which is just a setting that you determine in the simulation. It can't really be determined by theory. It's how discrete your problem is, basically. Their estimate changed by a factor of 3. And so if they went from 1 to 3 captured planets with one particular change of binning, but given how sensitive their estimate appeared to be, I would have liked to see a wide variety of bins checked and compared to the resulting value. Because if you go the other
Mhm.
way and it goes from 1.2 to zero point 0.3 or zero point 0.4 planets captured, then it's like, the conclusion of the study might have been totally different. It might have been it's very unlikely that we captured one instead of what it was, which was pushed in the media like there's likely to be a planet out there, or yeah. So because there's
Mhm.
quite a lot of media discussion about this, and so I think it was a very very interesting analysis, and I think there's absolutely a room to continue investigation.
As is the nature of most science.
Have you seen the JWST picture of Jupiter mass binary objects, which are a class of object related to this stuff?
I have, but you feel free to refresh my memory.
um, uh, so I just found them so cool and so weird because they're so literally in the Orion Nebula, JWST identified these objects that are literally pairs of planets just
Mhm.
floating around.
Yeah.
And it's like you can very clearly see that there's like these distinct planets, and it I find it the craziest thing ever. Like that we can even have achieved resolution to see pairs of planets in other like just so far away from Earth. I mean, the Orion Nebula is what
Yeah.
1,500 light years away.
That's incredible. So just to be clear, if you zoom in a wee bit and then follow follow them. The actual pairs of planets is these two, where you have control of the screen, but it's those two dots above it. That's right. There they are.
Yeah, yeah, and so you can see the zoom ins here. These are
Yeah.
distinct pairs, and it's like they're just so close to each other. I mean, obviously, talking cosmic distances, but like they're just so common and relatively close in the nebula. It's like, how do these form? Are they like, do they just form in free space from like the gas floating around in the nebula? Do they form in a solar system and then get ejected? Like,
Are they failed stars?
right.
Yeah, I can't remember the actual mass of these. I'm not sure the mass has yet been measured, but they could be essentially pairs or binaries of brown dwarfs, which are failed stars. So
Also,
if
I
they
think failed stars is a little chart. Why do I call them pre-success?
pre-success stars, there you go. Yeah, these brown dwarfs typically tend to be lower than 8% of the sun's mass. And downward, of course. So these are, I think they have to be 80 Jupiter masses and above to be called a brown dwarf. So I don't actually know the mass of these, but and it's
Well,
hard to tell.
in the name, they're Jupiter mass binary objects, so they're like comparable to Jupiter's mass.
Yeah, but they could be 5, 6, 8, or 10. I haven't seen the study. I suspect.
I know what you mean. It's like those ads where it's like, we deliver it to your home in minutes, and then it's like 500 minutes later.
That's right. That's right. That's right. You get your pizza in 25 minutes or less. Or how many integrals of 25 do you need? But, yeah, but still phenomenal to find them what is essentially free floating, very low mass objects. But of course, they could, as you say, they are pre-success or failed stars. Or they could be ejector from third body or multi-body interactions. Don't forget, we haven't seen these previously because this is an image that was taken in the far infrared or medium infrared at least, and so we're able to peer through the very extensive gas and dust cloud that is the Orion Nebula, stellar nursery, if you will.
Not to mention, I mean, these are very on the edge of JWST's resolution, and it's already enormous and bigger than anything we've had before. So,
it's incredible, yeah. And you can see actually in the top left of the image, this white horizontal bar is representing the scale, and it says 1170 AU, and we rightly said 1 astronomical unit is the mean distance between the Earth and the Sun. So this is something like 10, 20, nearly 30 times, this white line is 30 times the orbit of Pluto and the Sun, approximately. So these distances between these two objects here, for instance, this one here that's at the sort of 10:30, 11 o'clock position, is just enormous.
well, actually, it doesn't seem that. Yeah, I think it's actually the opposite.
Well, it must be 10 AU.
That you mean between the two?
Yeah. So
sorry.
10 AU is like the distance, say, from Saturn to the Sun.
Sorry, I thought you meant the distance between like the two objects, the parent distance there. No, yeah, that's that's quite large.
Yeah, that's incredible.
That quite substantial. But the distance, I mean, this is like probably roughly 2000 AU, which is like, I mean, if you started at the sun, 2000 AU is like you'd be out at the outermost edge of like the Oort cloud, right? At 2000 AU. You wouldn't be quite to the next star, but you'd be at the farthest edge of the
Yeah,
solar system.
yeah.
Yeah.
No, you definitely be
So
nowhere near the next star, but that's
so like having these pairs like within all basically a solar system distance of each other is kind of freaky.
well, you've got to be really careful here because this is a
Right.
2D
Because
image.
it's a
One could be in
projection
the
effect.
foreground, one could be in the background. Yeah,
Right.
the distance could actually be way farther.
It does look. I think I'm getting tricked because they look so comparable in size. Like the so my mind is like, oh, they're at the same. They're at the
Yeah,
same.
you actually don't know the orbital projection either. So
No.
it's, I mean, yeah, we have no sense of how close, unless they have, well, they can't have parallaxes. So yeah, we actually don't know the distance between the groups there.
I hope JWST makes a time lapse of one of these or something because that would be so cool.
That would be cool.
Although if they're at a distance of like Saturn, though, they'll probably make one orbit in like 30 years, like Saturn does, right? So
yes, that's right. And again, that's assuming if you're seeing them plane on, if they are perfectly circular, not orbital, elliptical. Although that shouldn't actually change the period, but still, but amazing.
it's remarkable, absolutely remarkable.
Oh, there you go. Actually, if you have a look down there, they have
There's a
mass
scale.
estimates. They have
Right
mass
there, yeah.
estimates.
Oh yeah, so you're right, like 3 to 7 Jupiter masses. It looks
Yeah,
like.
that sounds about right. So they're sort of they're right on the edge of being brown dwarfs. So they're super Jupiters or very low mass brown dwarfs.
They're steroid Jupiters.
This is a really good point for our viewers, however. So when you see something like this on an astronomical image that says 4 Jupiter masses or 3 Jupiter masses, almost always those are estimates or they're based on some theoretical stellar model. So we don't actually know the masses of them. They just appear to have the right brightness and color temperature to be the mass that we're talking about. But these masses could easily be a factor of 2 in error.
Since these are like Jupiter mass objects, relatively speaking. Up, sorry, Astro Puppy wants to join the conversation.
Astro Puppy.
Come here, pal. Since these are, yeah, he's tired after a long day of filming reels with no pay.
Another feeling.
Sorry, yeah, so factor 2. I'm wondering if these are planet-like objects, like sorry, even if they're brown dwarfs, is there a brown dwarf like mass because they're not glowing, right? We couldn't use a mass luminosity relation for it or anything, right?
No, well, you definitely couldn't do the luminosity unless you assume the mean distance to the Orion Nebula. But
Right.
no, these are actually they're just.
But what I mean is they're not nuclear fusing, so it's not like we can.
No.
Yeah,
That's
they're entirely being illuminated by reflected light from like the nearby stars.
No, that's not necessarily true. In the infrared, they are emitting because they're undergoing gravitational contraction.
Oh, right.
Just like Saturn and Jupiter, while most of the light we see is reflected sunlight, they themselves emit infrared light into space because of the internal energy due to contraction.
Right. I mean, effectively, we know that like even like the Earth has a hot core and stuff that's going to be emitting some level of thermal infrared.
It's probably very low. Don't forget by the time that hot core energy gets to the surface, it's so distributed. I mean, I don't know what the average surface temperature of the mantle is, but it's very low compared to the several thousand-degree core. But these are emitting their own infrared because they're undergoing gravitational contraction.
So like they're collapsing and it's being converted to heat.
Yeah, just through friction essentially, or conservation of energy as it collapses. But I mean, you can already tell in these images the next nearest star for some of these pairs is thousands of astronomical units away. There's no way their cloud decks could be illuminated by those stars that we would see them.
Okay,
so it's actually internal energy due to their contraction.
Okay.
I mean, don't forget the Orion Nebula, by the way, is about 1-2 million years old, perhaps. So these are very, very young stars or objects, and so even the star-like systems in this object, this nebula, they're not fully turned on stars yet because they're too young.
Okay. That makes sense, and it's kind of making me want to get an IR filter for the 6SE.
Well, if you do get your IR filter, you'll probably just pick up the irradiation or the emission of the filter itself.
Really?
Yeah, because don't forget your filter will be at, whatever observing conditions you are. Let's say even if it's 50 Fahrenheit, that's blazing away in the infrared.
Okay.
And also you don't have a detector to detect the infrared.
Oh, well, I mean, my CCD is sensitive to infrared, actually quite sensitive. I have a ZWO ASI 224MC.
How far out does it go? What's the transmission curve?
Oh, that's a good question. I don't know off the top of my head.
Yeah. I mean, even if it goes out to 10,000 Kelvin, which is the very, very near infrared, that's the sort of the best you could hope for. And don't forget, the night sky especially is blazing away in the infrared because of all those water molecules vibrating.
Yep. Okay. So
Yep.
Ixnay on the IR filter.
Yeah, I'd save you money. You're not going to detect anything.
I did get an IR cut filter though. And then I was so excited and I was so ready to use it, and then it proceeded to rain for a week straight. So, and we've had crap seeing since then.
Yeah. Well, don't forget, whenever water vapor turns into liquid water, you get a latent heat of vaporization released. So it'd be blazing away in the infrared.
Well, no. So I had an IR cut filter, not an IR pass filter.
Yeah, no, that's true. Okay.
Yeah.
So yeah.
So if anything, that should have helped.
Yeah, if anything, it would have helped. Note to self: don't use your telescope in the rain.
Yeah. That's, well, that was my plans for tonight.
Yeah.
Yeah, so I live in Santa Barbara where it rains like 10 to 20 days a year, and all of them fall when I get new telescope equipment. Every single time.
That's what it's like to be an astronomer.
It's not called the astrophotography forum isn't called clear nights for a reason. It's called cloudy nights.
That's right. Well, it's snowing here. I'm in Gloucester, Massachusetts, and it's snowing right now, so I won't be.
Yeah, how is the blizzard? I heard it was going to be really bad.
Yeah, it's pretty bad. It was pretty tame earlier on, but now we've got the several inches, and there's a fair bit of wind. But yeah, it's pretty outside, but I won't be observing tonight. That's for sure.
You know, they say that like after a storm, the seeing is the best, and I like saw that in many places. And then after a big rainstorm, I went out and tried to do some planetary observing, and it was garbage. And I feel like, is there some running joke in the astronomy community where you tell people that the best time to observe is right after rain, and then they go out and they're just disappointed?
Yeah, it's a complete myth, right? Because of course, if you've got any precipitation, the energy in the atmosphere was probably high, and so that means turbulence, which is
turbulence, right?
Seeing is bad turbulence, and so now you only get good seeing typically when you get good laminar flow of air, and that often is not associated with the after effects of bad weather.
I remember when you were observing, you were talking about laminar flow with, I think it was Alex or whoever it was. And I say it's really cool that these kinds of stuff impact your big, telescopes as well as just the consumer ones.
Oh yeah, it's actually nothing to do with the telescopes at all, really. It's to just do with the turbulence in the atmosphere.
Oh, but I mean, like, you think for some reason I feel like there's some mystique, like, oh, we put these big telescopes, huge mirrors, many times larger than like a celestron on top of like these high, super cold places, which I know it does help with the weather a bit, but they're still subject to like the same effects at the end of the day. And it's yeah.
Well, in fact, that's a large part of why we put telescopes on these places. So, for instance, the telescopes on top of Mauna Kea in Hawaii. One of the principal reasons is you get this beautiful laminar flow coming off the Pacific. So all the wind or air movement contours are very linear, very non-turbulent. And so you get very, very good seeing. And it's the same for all the telescopes in Chile. You get that laminar flow coming in off the South Pacific, and it's just wonderful for the seeing. Wonderful.
Interesting. So where I usually go observing is like at the foot of a mountain, which is next to the ocean. So that sounds like could be the worst possible location, right? Because you'll have the flow from the water folding back over itself multiple times.
Yes, basically. Yeah.
Interesting.
Yeah.
That's good.
Sorry about that. Well, you live where you live.
Yeah. Reasons for leaving Santa Barbara. Seeing was bad.
Yeah.
This is the houses here are too expensive for the terrible seeing you get.
Well, there you go. That could be a good selling point for astrophotographers.
I want that on Zillow, like a freaking astronomical seeing category.
Most people are thinking, what the heck is this person doing?